All right, we're into psychrometrics, the study of moist air. Make sure that you remember there's how many humidities that you really need to become familiar with, and how many temperatures. That's right, temperature dry bulb, temperature wet bulb, and the last one, dew point, and the two humidities, the relative, and then the brand new humidity, probably few of you were ever exposed to, is humidity ratio. Humidity ratio. All right, what type of balances have we done with moist air mixtures? Yeah, so you have two mass balances. One is of the dry air, and one is of the water. So you have a water mass balance and a dry air mass balance. And then we're going to have energy balance. Last time I talked about justifying the assumption that water vapor behaves as an ideal gas, even in saturated air, at relatively high temperatures. And we justified it by saying that the specific volume from some experimental measurements or from some tables or for some source that doesn't depend on ideal gas assumption, we compare that with the ideal gas estimate of the specific volume, and we normalize that. That's our error. Maybe take an absolute value of that. And then we said, for a lot of cases, this is less than maybe 0.2%. I think it was less than 0.1% for this condition. It's a very small error. So one thing I did do was I took and compared the ideal gas approximation with the data out of the code RefProp for water vapor. And we plot it on a traditional temperature specific volume diagram. So you see the dome, and so at the top of the dome, what point is that? At the top of the dome? Critical point, right. Notice also on the x-axis for the specific volume, we don't plot it linear scale, we plot it on a logarithmic scale because the variation is so large. And so this is actually data that's plotted here. So you can see this is 10 to the 2, 10 to the 3, 10 to the 1, 10 to the 0, etc. Here is a low pressure, 2 kilopascal, and often our moist air mixtures, the vapor pressure is very low. It could be down in that 2 kilopascal region, often is. And what we find is that this is 100 kilopascal. I know that way up in here, this is not relevant for moist air mixtures. It's way down in here that's relevant for moist air mixtures, okay? And what we find was I calculate the error as the absolute value of the specific volume from the code RefProp, which is based on experimental observations, compared to the ideal gas specific volume, where you're just using the ideal gas equation, R bar T divided by P molar mass. And then we plot where this error is less than 0.1%. Everything, this is where it is 0.1%, all the way down to saturated vapor, and everything to the right of that curve, it's less than 0.1%. Very low. I didn't try to find 0.05% or 0.01%. I mean, that would be ridiculous. And then you can see the 0.25% and 0.5%. This is all very good assumptions of ideal gas model for a whole range of conditions, which is even up to saturated vapor at those low temperatures and low pressures. Now we're going to deal with an energy balance. So we have moist air coming in and moist air coming out. We have the dry bulb temperature in, we have the relative humidity in, we have the humidity ratio in. You could have other characteristics. And what we want to know is when we do an energy balance, we want to have some energy flow into our system. Let's say there's also some heat transfer, Q dot, into the system. And then it flows out at state 2. So in at state 1, out at state 2, what would our energy balance look like? It'd be some mass flow rate times some enthalpy coming in plus some rate of heat transfer coming in equal to some mass flow rate enthalpy going out. True? Well, this mixture is made up of the mass flow rate of vapor times the enthalpy of vapor, and we'll call it H of G because that's the way you look up the enthalpy of vapor. You get the enthalpy of saturated vapor at that temperature from the tables. And then you have the mass flow rate of the dry air times the enthalpy of the dry air coming in. True? Plus the rate of heat transfer added, maybe there's a heating coil. And then the same thing, mass flow rate of the vapor going out. This is in, going out. You have the enthalpy of the vapor going out. And you have the mass flow rate of dry air going out. And the enthalpy of the dry air going out. Now, for a single inlet of the air and single outlet, there's no splitting, so the mass flow rates of the dry air are the same. But if you had a source of water, m dot liquid, how would you add that into the energy balance equation? Well, wouldn't it be another in over here? We'd have the mass flow rate of the liquid coming in plus that enthalpy of the liquid coming in. That would be saturated. It's coming in a liquid state, saturated liquid at whatever temperature it's coming in. True? Wouldn't that be how you adjust? And so you'd have to bring that down also to this equation right here. All right. Well, if you divide through the equation, there's a couple of different ways to manipulate it, but if you want, you can have the mass flow rate of the liquid times the enthalpy of saturated liquid plus, I'm going to focus on this term, the enthalpy of the vapor coming in times the humidity ratio coming in times the mass flow rate of the dry air. Isn't this product right here the mass flow rate of the vapor coming in? Yeah. And then what you can do is group those two terms such that this is the enthalpy of the dry air coming in. Both of those multiplied by the mass flow rate of the dry air. Add in the heat transfer, and the other side looks the same. You have the enthalpy of the vapor going out, humidity ratio going out, and the enthalpy of the dry air going out times the mass flow rate of the dry air. A lot of times we'll talk about a mixture enthalpy, which is the combination of the dry air plus the vapor's enthalpy. And it's all on a per unit mass of dry air. This mixture enthalpy is a combination of both terms, and it has units of kilojoules per kilogram of dry air. Before you get to use the mixture enthalpy a lot, I encourage you to avoid using the mixture enthalpy and do it paying attention to what's happening exactly to the vapor, what's happening to the water if it's coming in liquid or leaving liquid, etc. Okay? Because you can do it that way, and I think it builds more insight into it. Next, the psychrometric chart, they're going to plot the mixture enthalpy. Same with the liquid, you could add it to the other side, which would be subtracting it from the left-hand side if it's condensate. Air at 12 degrees C and 30 cubic meters per minute and 30% relative humidity is heated and humidified. To start to organize our information, we have the volumetric flow rate coming in is 30 meters cubed per minute. I'm going to pause a little bit. 30 meters cubed of what? 30 meters cubed of dry air, 30 meters cubed of moisture, 30 meters cubed of moist air, which is a combination of dry air and water vapor. Which one is it? It's the combination. It's the combination, okay? All right, and then it's relative humidity coming in is 30%. It's going to be heated. Typically, we'll have a hot coil, hot water in the coil, and so as it flows over the hot surface, the air temperature will go up. The moist air temperature will go up. Okay. And then it's going to be humidified. Well, how do you handle humidification? A lot of times you bring in some water and you spray it into the airflow. So this is like a mister spraying in water. Now, you can bring in water in a lot of conditions. You can bring in liquid water that's relatively cold and spray it in. Or you could even bring in steam vapor, very high temperature vapor, water, and spray it in. We have to continue to read to see what they're bringing in for this application. It exits at a temperature of 32, so it's exiting at T2 of 32 degrees C and Phi2 of 40% relative humidity. Liquid water at 25 C is supplied to the humidifier, not saturated vapor at 25 C or saturated vapor at 100 degrees C. If you had a boiler, you could easily do that for humidification. And if you're up north in Chicago and New York, you got long winters, you probably have a boiler and you're going to humidify with steam. This is liquid water at 25 degrees C. The pressure is 101.3 kilopascals throughout. Determine the mass flow rate of the dry air entering the coil in kilograms per minute. So what symbol are we looking for? Mass flow rate, dry air, m dot, subscript dA in units of kilograms per minute. So how are we going to solve for m dot dA? We have the volumetric flow rate coming in, AV coming in, and if you could calculate the specific volume of the dry air in the moist air mixture, you would either multiply by the specific volume of dry air in the moist air mixture or divide by the specific volume. Which one is it? Everybody needs to make sure and answer that question in their own mind. I know some of you are on top of it, which is good. But how can you tell? How can you, if you say, ooh, how do I remember this? Remember your units. Check your units, right? And so the units are, for this term, it's meters cubed per minute, right? And this one would be meters cubed per kilogram for the specific volume. And that would give us, oh, good, the kilograms per minute that we're looking for. How are we going to calculate this specific volume of the dry air in the inlet mixture? Use the ideal gas equation. R bar T1 divided by the molar mass of the dry air and the partial pressure of the dry air in the inlet mixture. Or is that the total pressure? Which one is it? It's the partial pressure. How do I calculate the partial pressure of the dry air in the inlet mixture? It's the total pressure, which is 101.3 kilopascal, minus the vapor pressure on the inlet. See, it's almost like, okay, you got a chain reaction here. I know what I want to calculate. Oh, I need this information. Oh, to calculate that, I need this information. To calculate that, I need this information. So how do I calculate PV of 1, the actual vapor pressure coming in? Phi1 times the saturation pressure at the inlet temperature. And finally, we're here where we can start to say, oh, sure, this is 30%, and the saturation pressure at the inlet temperature, it's 1.403 kilopascal. Great. Then we get PV. Then you come down here, you get the partial pressure of the dry air coming in. It's 100.88 kilopascal. You get the specific volume of the dry air, 0.81078 meters cubed per kilogram. And then finally we get the mass flow rate of the dry air. I'm going to put the answer up here so I can box it. It's right at 37.0 kilograms per minute. For part B, we want the flow rate of liquid water supplied to the humidifier. What symbol do we want to calculate? What are we looking for? M dot liquid? How am I going to solve for part B? Introduce a control volume, and I'm going to do a balance. What type of balance? For the mass flow rate of liquid water supplied, just probably a water balance. Just a liquid, but it's not liquid. It's water as an entity. Some of it's liquid coming in, a lot of it's vapor coming in, a lot of it's vapor going out. So when we do our water balance, we have the mass flow rate of dry air coming in times the humidity ratio coming in. Is that our mass flow rate of vapor coming in? Plus the mass flow rate of liquid coming in. Those are my two ends. And then we have the mass flow rate of dry air going out times the humidity ratio going out. Does that work for a water balance? So the mass flow rate of the liquid is equal to the mass flow rate of dry air times omega 2 minus omega 1. Did I just calculate the mass flow rate of dry air? Yep. How about the humidity ratio inlet and the humidity ratio outlet? I need to calculate those. So how do I calculate omega inlet? That's right. You know that it's a ratio of the mass of vapor to the mass of dry air, and it behaves as an ideal gas. You look at the same volume and you get a nice relationship, 0.622, which is simply the ratio molar masses. It's the ratio molar mass of water vapor divided by the dry air molar mass, times the partial pressure of the vapor and the partial pressure of the dry air. And that's all inlet, inlet. We calculated those, so we find that this humidity ratio coming in is 0.0026. It's dimensionless. Sometimes I like to put kilogram vapor per kilogram dry air. Now, how about omega 2 on the exit? Well, it's the same 0.622 PV on the exit divided by partial pressure dry air on the exit. I have to go calculate those, right? So what's the partial pressure of the vapor on the exit? Relative humidity on the exit times P sat on the exit. And it's going out at 32. Okay, so we can calculate the partial pressure of the vapor going out, 1.904 kilopascal. And then we can calculate the partial pressure of the dry air going out. It's 99.40 kilopascal. Then we can come up and we can calculate omega 2, and it's 0.0119 kilogram vapor per kilogram dry air. Now we can return to the mass flow rate of the liquid equation, and we calculate the mass flow rate of the liquid to be 0.345 kilograms per minute. Now, the rate of heat transfer to the moist air. So now we're looking for Q dot that's really coming from that hot water in our heating coil. What's the rate of heat transfer from the heating coil into our air? But that's what we're looking to calculate. Q dot, units of kilojoules. How am I going to do that? I'm going to do an energy balance for the same control volume. There, we'll use the bottom of the next top page. So if I do an energy balance here, I'm going to have the enthalpy of the dry air coming in plus the enthalpy of the vapor coming in. I'm going to write it H of G, vapor coming in, times the humidity ratio coming in, times the mass flow rate of dry air coming in. So that's the inflow with the moist air coming in. The energy is a contribution from the dry air as well as the vapor that's in the moist air. Okay. Then we have Q dot, what we're asked to calculate. That's an in. Do I have any other ins into this control volume? The liquid. And so we have the H of F, whatever temperature that saturated liquid's coming in, it's coming in at 25 degrees C. Okay. Times the mass flow rate of the liquid coming in. We just calculated that, did we not? So we have that calculated. Those are all the energy flows in with mass as well as with the heat transfer. How about the out? We have the enthalpy of the dry air out plus the enthalpy of the vapor out times the humidity ratio out times the mass flow rate of dry air. At this point, sometimes you want to eliminate m dot dry air, but we already calculated this from part A. We calculated this from part B. So a lot of those are like, okay, check, I've got those. How about this? Humidity omega outlet. Oh yeah, we already calculated those, didn't we? What we're left to do is calculate the vapor's enthalpy coming in. Well, that's coming in at 12 degrees C. So this is just H of G at 12 degrees C. It's a 2522 kilojoules per kilogram. What is H of G going out? Well, that's the enthalpy of the vapor going out at 32 degrees C. That's 2559 kilojoules per kilogram. Get them from the tables. We're pulling from a RefProp type of software. What about H of F? Saturated liquid at 25 degrees C, 105 kilojoules per kilogram. A lot of times that small can be neglected. It's not a large mass flow rate, and it's not a large enthalpy. But let's include it here. Now, how do I handle this enthalpy of the dry air? Yeah, it's a specific heat times the temperature. And what's happening is you can a lot of times rearrange it. Do it this way. Take this term here and bring it over to this side such that you have H dry air 2 minus H dry air 1. That's C sub P of the dry air times the exit temperature minus the inlet temperature. C sub P, 1.005 kilojoules per kilogram Kelvin or degree C, times the change in temperature. You know the two temperatures. It comes in at 12 and goes out at 32 degrees C. Degrees C and Kelvin cancel because it's a temperature change. All right, so we can now calculate Q dot, and we find that Q dot's equal to a total of 26.5 or 26.6 kilowatts. It's into the system. Yeah, it's shown into the system, and so it's positive. If I look at how much heat was required to heat the dry air, the equation for that is the C sub P of the dry air, delta T of the dry air, times the mass flow rate of the dry air. I calculate the mass, that energy, just to heat up the dry air, about 12.4 kilowatts. That means the rest of this heat went into Q dot, went into heating up the vapor that went through the system, and then the rest of it went into not just heating up the vapor, but helping the liquid become vapor. So what does the equation for just heating up the vapor that comes in with the system? That's going to be the H of G exiting minus H of G inlet times omega 1 times m dot dry air. See, it's like I brought in some water vapor, and just like the dry air, I just heated it up. Great. So I'm going to erase a little bit here, well, I'm running out of room. Let me just erase this. And when you calculate this, it didn't take a whole lot of energy to heat up the vapor that came into the system. It took 0.06 kilowatts. There's a lot of energy that went into taking and helping the liquid water, which was sprayed in to the system, become vapor. So what is that rate of heat transfer, that component of this Q dot N? Isn't that the H of G2 minus H of F coming in times omega 2 minus omega 1? That's how much, well, if you can multiply this just by m dot liquid. And that amount is a whopping 14.10 kilowatts. We find that the Q dot, 100% of the Q dot that comes in, that 47% or thereabouts went into heating the dry air. Around 0.2% that went to heating the moisture that was already in the humid air that came in the system. And a whopping 53% or 53.1% goes into vaporizing the liquid water that came in. This is what we call sensible heat, sensible heating. The heat that was added was realized by a change in temperature of the dry air. It makes sense. This is old terminology. It goes way back in the, 1700s. And then you have latent heat. What's latent mean? Hidden heat. It really doesn't make sense when you first look at it. If I dump heat into something, the temperature must go up. But you know from thermodynamics that you can dump heat into something and the temperature really doesn't go up because it changes phase. It boils. And it takes a lot of energy to change phase. And often it doesn't have a big temperature change. So this part right here is due to the vaporization. Now I know that there's a little difference because it's 25 degrees and then it comes out at 32 degrees C. So I could have separated out and said how much energy did it take to heat the liquid water from 25 to 32 and then finally from 32 vapor to liquid to vapor. But this is almost all of it liquid to vapor. And so that's the latent. How many people have heard those terms? Latent, sensible? Not enough hands are up. Does it make sense? I know it's old terminology, but it's widely used in engineering. And I've seen a lot of young engineers they start a job or a vocation in the HVAC industry working for a consulting company, and they'll mess up their calculations because in their mind they either forget about the latent load or they double count for the latent load. I've seen both of them. And they just I bring in air into my building, I do this to it, I heat it up or cool it off, the moisture content changes, sure, but this is how much heat is needed in the cooling coil or heating coil to accomplish this. And if you would have not taken into account the amount of heat needed to vaporize the liquid water, you'd have been off by about a factor of 2. I want to talk about an adiabatic saturator. So an adiabatic saturator is a means by which you can make a measure the pressure, like the gas pressure outside, 101.3 kilopascal. That's pretty easy to do. You can make one pressure measurement and 2 temperature measurements. You can measure the inlet temperature T1 to this device called an adiabatic saturator. And you can measure the outlet temperature T2 from this device. And if you just know those 3 pieces of information and you know that it's doing a certain job, it's an adiabatic saturator, and I think both of those words you can piece through in your mind to figure out what this device is going to do. You can go back and you can infer the amount of moisture in the inlet air, either the humidity ratio or the relative humidity of the moist air coming in. So here's our device. It's called an adiabatic saturator, and we just measure the inlet dry bulb temperature, the exit dry bulb temperature, and we know the pressure, atmospheric pressure. And from those 3 measurements, one is so trivial I hate to even list it, pressure, you can infer omega and phi. How does this work? Well, let's take a look at the words. What does this word adiabatic mean to you? No heat transfer. So is there any Q dot with this black box called the adiabatic saturator? No, it's well insulated. No heat transfer with the surroundings. But it's a saturator. Now, what does the word saturator mean to you? It makes the air saturated. It makes what's coming out of it. Can you describe? The assumption is it's going to do something to the air coming out such that the air that comes out is saturated air. So this is saturated air coming out. What is saturated air? 100% relative humidity. Phi2 is equal to 100%. I know what PV is. PV is Psat at the exit temperature T2. Hence, I know the P of the dry air, that's the total pressure minus PV. Hence, I know the omega out, that's 0.622. PV over P dry air out. True? This is out, this is out. So once you've determined that it's saturated air and you know the temperature and the total pressure, you know the relative humidity, you know the humidity ratio going out. If you're going to come out with saturated air, you have to supply to it. Not only do you have to supply moist air coming in, which is not saturated, and you're going to infer the humidity, relative humidity, and humidity ratio of that moist air from these calculations, but what else are you going to have to supply to that box? You're going to have to supply some water. And often that is like a makeup water or to help it become saturated air, and often this comes in as liquid water. So for the adiabatic saturator to develop these almost magical equations so that you can calculate phi and omega on the inlet stream, what type of balances do you need to do? Mass balance, dry air mass balance, water mass balance. So 2 mass balances plus an energy balance. That's all you have to do. The math will work itself out. You rearrange it cleverly to get an expression for omega 2. So let's go ahead and just get the equation here. So if I have a control volume, we have the air balance. It's so trivial. M dot dry air in is equal to M dot dry air out. You have the inlet stream 1, outlet stream 2. Okay, so that's done. The water balance. Omega 1 times M dot dry air plus M dot liquid equal to omega 2 M dot dry air. So we can rearrange this equation because we're going to use it to eliminate M dot liquid in the energy balance. It's going to be omega 2 minus omega 1 times M dot dry air. So we've done with our mass balances. Now let's do the energy balance. H of G coming in times omega 1 coming in plus H dry air coming in times the mass flow rate of dry air. Is that all the energy flowing in with the with the air inlet moist air? We express it as a multiple of M dot dry air, right? Then we have H of F times M dot liquid. Guess what we're going to eliminate? This right here is going to go right there in a second. Let me finish the equation though. What about going out? H of G going out, omega 2 plus H dry air going out times M dot dry air. Cancel M dot dry air. It's in all of the terms. Cancel M dot dry air here, cancel it there, cancel it there. And so I rewrite and I have that H of G1 omega 1 plus H of dry air 1 plus H of F times omega 2 minus omega 1 is equal to H of G2 omega 2 plus H of dry air 2. Get those dry airs together. Get this one to the other side. Get all of the omega 1s on one side and everything else on the other side. And so what I'll pick up is I'll pick up omega 1 times H of G1 minus H of F equal to H of G2 omega 2 plus H dry air 2 minus H dry air 1 minus H of F times omega 2. Did I do the math right? Get rid of this red line, it's confusing. Does the math look right? We're there then. All you have to do is say, here's the equation, omega 1. The inlet humidity ratio can be calculated knowing the vapor enthalpy going out, saturated vapor, times omega 2 going out, plus, or depending how you want to write it, plus, a lot of times I'll put something like this, C sub P of the dry air times T2 minus T1. It's a change in the enthalpy of the dry air, minus H of F omega 2 divided by H of G1 minus H of F. Once you have omega 1, a little bit of work, you can work back to get phi 1, relative humidity. So I pause and we look back at what we were able to reestablish. I know that this is done in the textbook, been done in engineering and science for a long time, this notion of an adiabatic saturator, but just making temperature measurements and knowing the pressure and knowing that it's saturated air coming out and knowing the condition of liquid water coming in, then you can infer the humidity of the inlet air. Adiabatic saturator has inlet air of 25 degrees C and 100 kilopascal. So here's our condition. It comes in at 1, temperature 125 degrees C, and it goes out at 2 of 20 degrees C. And it's always 100 kilopascal. Okay, great. Determine the humidity ratio of the inlet air. So I want to find omega 1. And then I want to find the relative humidity of the inlet air, phi1. We just established the equation that I need to use. I don't want to rederive it. I just want to be able to apply it. There's no information about how the liquid is supplied. And often it's supplied at a temperature. If you don't know anything, pick it to be the outlet temperature. At the temperature of the liquid coming in is like 20 degrees C. Calculate omega 1. You have the enthalpy, let me write it this way, C sub P, T2 minus T1 of the dry air, plus omega 2 times H of G2 minus H of F. And then we divide by H of G minus the H of F. These are known right away. That's known right away. H of G going out at 20 degrees C, we can look that up right away. H of 1 coming in at 25 degrees C, H of G coming in at 25. This H of F, we'll assume it's 20 degrees C. And so the only one that's difficult is the omega 2, it goes out saturated air. And so we've done those equations before, so omega 2 is 0.622 PV2 divided by P dry air 2. PV2 is equal to P sat at the temperature T2. P dry air at 2 is equal to P minus PV2. So all of those wrap up and you get it. So for this problem, omega 1 is 0.0128 kilograms of vapor per kilogram of dry air. I'll just leave it like that. How do you calculate phi1? So it's the PV over the P sat. How do I get PV? This is a challenge. In the interest of time, I'll say that you have to unravel the humidity ratio equation that omega is equal to 0.622 times PV over P minus PV. Okay? And it's like, now I know omega and I know P, but I don't know PV from that equation. So I have to unravel that equation to get PV to work backwards. So PV is equal to the pressure times the humidity ratio divided by 0.622 plus the humidity ratio if I did the algebra correct. And now that you have PV, you can calculate the relative humidity on the inlet, and we find that the relative humidity is 63.6%. Thank you for your attention. We'll see you Friday.